All right, let's do this. This is lab 4, and in this lab, we were assigned to create 4 different programs, 3 of them in assembly, and one of them is going to be in C. And for these programs, the first one was we had to write an MSP 430 assembly program that performs a bitwise NAND operation and with the 8-bit values in R7 and R8 and keeps the results in R8. So that is what we have in front of me right now is the program that I wrote that essentially takes the NAND and the values of R7 and R8. It goes through the NAND logic controller and the result is saved then in R8. To watch this, we're going to pull up the debugger and our breakpoint is set at the reset. And we're going to go down and watch it. Now, I find that this is better to understand it with binary. It's going to be a little bit easier to see the actual NANDed process. Here we go. It's going to store, these are some random values that I set up that I'm pulling directly from the memory cores and putting those directly into the value of R7 and R8, storing those values. So we'll watch that. And here we go. In R7, here's our value 10100010. We're only worried about the first 8 because we're only dealing with moving these bytes.b's. So that only deals with the 8 least significant figures. And so then now here it sets up the R7 and the R8 for the operation. So what should we expect to see in the next is we should see in R8 we should see a bunch of 1s and then only 1 0 right here where I have my thing in it. Because that's the NAND operation happening is anytime that there's a 1 and a 1 added together, it'll be a 0. But then anything else is going to be any other combination is going to be a 1. So we'll see that. And yep, there we go. As you can see, everything else is a 0. That's actually, it should be flipped. Wait, yeah, there it goes. It was just setting it up. And then, yeah, and right here we're in is Izar trap. I thought I put an NOP right here, but I just don't understand the process very well. I was under the impression that that would stop it from going to the ISR trap. But yeah, that is the first program. There we go. Okay, so now let's stop that. Let's go to our second program. So for this, we had to write the MSP430 assembly program. It's going to use rotate, jump, and increment instructions to count numbers of bits that have the value of 1 in the lower byte of the R7 register. This count should end up in R8. Cool. So this is going to... Let's run this. So this is just showing off the different instructions that we can use to manipulate the numbers that are stored in these values. As you can see in the pre-setup, I've added some of these rows. This is going to clear the value stored at R8, so it starts at 0. This is going to set R10 to become an 8-bit counter with 8 numbers. It's going to do 8 bits, single bits, one at a time, and count that down to 0. And then this is SR is going to set the individual amount of that counter for 1 bit 8 times. So let's step into, this is just setting it all up. All right, so here's our rotate to the right, the least significant bit in our R7. So see our R7 10010B. Let's see what that does. That should move that 1 over 1 to the right. And it did. Cool. As you can see, those 1s all went over. And Next, we should see R8, which is 0. That should get a 1. And bam. And then now we should see R10. That should lose that. That should just change to 0, and the rest should be 1s in R10. Oh yeah, it'll happen here. There we go. See? And there it's counting down. And we're seeing as R7, it's taking 1 bit from R7, adding that increment to R8, and then removing the counter from R10 here. Bam. And we're jumping back up to the main. I'm not sure how to use the jump correctly for this program. I did set it so after we go through the counter, after R10 is out of numbers here, let's see, we're at 4, 3, 2, 1. This is going to keep this jump that I set up here is going to keep the program here. It won't let me continue forward. That works a little bit better than an NOP. So we'll go forward and we'll go look at the C code that we had to do. So for the C code here, we have to, instead of watching our registers, I'm not sure how to set this up to where we can mess with the registers like we can with assembly, but we can set up these volatile unassigned integers in our expressions. So we're going to stop the existing program and we're going to run the C code. And what this C code is the C program. We're going to proceed with that. And what this assembly program, or sorry, this C program is, it's going to take the value of an nth triangle number, Tn, and it's going to calculate the same way that a factorial does, but instead of multiplying the nth values, it's going to add incrementally the nth values. So, for instance, the number that we're going to use is 8. So it should be 8 plus 7 plus 6 plus 5 plus 4 plus 3 plus 2 plus 1. And I can't even do math that well to be able to tell you what that could be, but that's why this program here is going to tell me. So we're going to set this up, set our timer up. Now this is going to set the counter to the value of nth. And then this is going to set the base address to 0. Oh yeah, variables. So there we go. Our counter is now set up at number 8. As you can see, num is 8. And there's our counter. And then here's our sum value. We've set our sum to 0. And then now we're going to run through this counter. So that should go to 8. Yep. And then now that's taking away 1 from the counter. And then it's 7, 15, 21. It's taken away. Go. It's a pretty neat little program. 33, and then 35, and then 36. And then bam, that should be it. And return 0 ends program. Perfect. And now that program is done. And then for our last program, we were supposed to do the exact same thing that we did in our C program, but do it in assembly. And this one is kind of interesting because we had to use the memory allocation or the RAM, and we had to set up some pre-existing values. So right here, we set up num, and that's going to be a dot word, and we set that value at 3. That's going to be our nth base number, and then we have our try, which that's going to be your actual output number. So we should see this be a 3 plus 2 plus 1, which is going to get us 6. And we're going to watch that in the register here. As you can see, I also had to set up these values up here in the pre. the pre-main loop. And yeah, we're gonna watch this counter go down and edit. Oh, crap, we're still in the C program. Let's terminate that. Okay, let's run the debugger here. Go, got our watchdog timer set. So here we're going to set our R5 to our pre-existing num in our RAM. So we're going to set our R5 to 3, and let's watch this in hexadecimal. It's a little bit easier to observe this in hex. Yeah, so now R5 is now 3. No, it's still 8. Yes, now it's 3. There we go. And then we're going to clear our value for 6. So 6 is going to be where our output is. And then we are going to test it at 0. It will, it should end the program. Okay, here we go. If 0, ends loop, definitely. And then bam, we add R5 to our R6. There we go. R6 is now 3. And then here's our repeater, our jump function. It's going to take away 1 from there. So bam, 2 is added to 3, and then 1 is taking away. Decrement, it means subtract. It goes down. Here we go. So our counter's still not at 0. It's still at 1. And then bam, adds to 6. Goes to 0 now. That's testing it. Bam. And as you can see, now that R5 is at 0, it's going to send us to store results. It's going to jump down to that. And then now we can save the new R6 into our tri-RAM address. And then we can stop the program from going forward. And yeah, here we go at the end program screen. And yeah, these were my 4 different programs for Lab 4. I had a pretty good time with all of them. The only one that I had a trouble with was expressing this jump function here in the second program, but I'm sure I will figure that out. Anyway, you have a good rest of your day. Bye-bye.